In this example, we'll try to evaluate the Fourier transform of a 8 sample sequence, and xn is periodic. So I'll show you the sequence first. I'll give you a sequence in this form as a list of numbers, and we'll tell you where n equals to 0 is by putting this little arrow. We can also, of course, plot this, and here is the repeating sequence. We're asked to find the DFT, DTFS, and DTFT of the above sequence. Let's examine the DFT first. In the DFT, just remember this equation. X of k, the DFT coefficients, is defined as this. Using the sequence small x of n multiplying by e minus j 2 pi over n, capital N, times k times n. You can then evaluate this for any of the xk, and typically we only want to evaluate small k equals to 0, 2, and minus 1. Now in this example, capital N is equals to 8. So when we expand this formula from here to here, we see each of these terms. Now, look carefully at the term. This is k equals to, this is little n equals to 0, little n equals to 1, little n equals to 2, 3, 4, 5, 6, and 7. That's it. The k, I'll use pink now, remains here as the parameter. So you have to change the k when you're evaluating for different k. What about the small x 0, 1, 2? Well, you substitute this value. x0 is 0. So now let's use a blue. This guy is 0. This guy is 1. This guy is minus 3 over 2. This guy is 0, 0, 0, 0, 0. So basically, we have reduced this equation into here. So we have 1 e minus j 2 pi over 8 k times 1. Here is k times 2. Minus 3 over 2 e minus j 2 pi over 8 k times 2. We work it out. For different k's, this is the answer. You can very quickly check whether this answer is correct or not by simply using FFT and putting the sequence. Please remember, x0 is 0. This is x0. Okay, this is x1 and this is x2. And of course here is x of 7. So now that we have xk, it is very easy to find ck, the DTFS coefficient. ck is nothing but 1 over n of xk. So in the next slide, we have this, and simply you take the xk and divide it by n, which is n equals to 8 in our example, and voila, you get this. This is the rectangular form of the DTFS coefficient. We want you to plot the magnitude and phase later on, and you have to convert the rectangular form into the polar form or the complex exponential form. Minus 0.0625 plus j0 is magnitude 0.0625. The minus becomes a phase of 180 degrees pi. Okay, this guy converts to this guy, and so on and so forth. So now we have the magnitude here, and we have the phase here. So all you need now is to plot the magnitude and the phase with respect to different k's if you want to plot magnitude and phase response. In this question, we are only going to plot the let's just only plot the DTFT. So the DTFT, to go from the DTFS coefficient, so the DTFT, in this case, because x of n is periodic, x of omega, even though it is from 0 to 2 pi continuous, or from minus pi to pi, up to you, continuous, because small x of n is periodic, only frequencies that is 2 pi over n times k has values. The rest has no values. This is because DTFS already tells us that only the harmonic 2 pi over n times k is of interest. That's why xk is non-zero. So in the DTFT, once we have ck, for periodic sequence, all we do is we multiply ck by 2 pi and put direct deltas at this frequency. So let's take a look. Let's take a look at how we're going to plot C0 first. The magnitude is 0.0625 at k equals to 0. So we draw a horizontal axis here for k. And in parallel, if you really want to draw x of omega, then simply at k equals to 0 is 2 pi over 8 times 0. K equals to 1 over here is 2 pi over 8 times 1, which is pi over 4 radian. K equals to 2, k equals to 3, so on and so forth are the corresponding continuous frequency omega. So the first value of magnitude is 0.06 with a phase of pi. See? 0.0625 with a phase of pi. The second one is 0.13 with a phase of 0.84. So k equals to 1, 0.13 with a phase of 0.84. The rest you can fill it up by yourself, and you will see that this is how we draw the DTFT magnitude and phase spectra. Remember, we need the deltas. So to show that it is deltas, we show them as arrows going up to infinity. And now you see how we go from ck's to x of omega through this process. Thank you.